Hello, I'm Steven Forrester. I'm the Principal Engineer of DMA Engineering. And in this video, I'll be talking a little bit about radiant floor systems. One of the things that we get asked a lot when we're involved in a design process is what type of radiant floor system should we use? A lot of times the design team may not know the differences between a high mass system and a low mass system, and what's the benefits of those two types of systems, or what's the pros and cons of those two types of systems. So we did a little bit of an analysis on the different types of systems here using a software package, doing a finite element analysis, or FEA. So just kind of want to dive right into this short little presentation. I'm hoping that I can keep it under 15 minutes without talking too fast. Sometimes I talk a little too fast. I'm going to try to dial it down a bit, see what we get. All right, so let's just dive into the different types of radiant floor systems. Probably the most familiar type of radiant floor system that most people are familiar with is concrete type system, right? This is the one that's been around probably the longest. And so this is, you just do a regular framed floor or what have you, slab on grade, and then put the tubing in and then pour the concrete over the top, and then put your surface, whatever you're going to put over the top of it. On that. The second most common that most people may be familiar with was staple up. I think staple up, I said that lightweight concrete may have been the first. That may not have been true, but staple up has been around for a while as well. And so this just goes right in the joist base, stuff at full insulation, and there's the radiant floor system. And the two more advanced type systems is staple up with heat emission plates. I would say this is a step above what the staple up is as far as technology goes, and then it takes it even one step further, and we call this a warm board type system, just using a trade name there. But this is just that subfloor with the aluminum plate stuffed into it, aluminum imprate layer over the top that's pressed into the subfloor with the grooves already in it. So then you just lay the tubing into that type of systems. I would consider the staple up system and the concrete system to be a high mass system. And then I would consider the warm board and the heat emission plates to be a little bit of a low mass system. And I'll show you why I say that as we go through the slides. So again, we used an FEA package to model these two types of systems. And here's the staple up model that we used. And the model's fairly similar across all the runs. So I'm not going to describe it once, and then we can just see the differences. So we have a 5/8 gypsum ceiling. So this was, first floor or a basement, or second floor floor. And this is the first floor here. Then here is the 3/4 inch subfloor, 3/4 inch plywood. And then we're just modeling a 3/4 inch hardwood as our finished surface. And then up here is the room. And so we just have a standard floor joist type frame. So here's the tubing for the staple up inside here. And then we have the fiberglass insulation stuffed into the cavity, which should happen on all radiant floor systems. You should have some insulation in there. Otherwise, it's not going to perform as well. So then pretty straightforward construction that's pretty common in wood frame construction. So let's look at the results of this. So this is a 170-degree supply water temperature. So this is a boiler system, be it gas, electric, propane, what have you. That's what it's going to be supplying, that water temp. Heat pumps can't do water at that temperature. So with that, we look at the floor surface temperature, and we see we got spots of 80 degrees, and then we got big voids in here where the surface is not uniform. And then if we look at the heat output, so on the left here is temperature. So this is a top view, and this is a side view. This view is what we're seeing there. And then top view, and this side here is temperature. And then this side here is the heat output that we're getting through it. So as I mentioned, I consider staple up to be a high mass system. And I say that because if you look at the temperature build up here, there's a lot of temperature build up in the floor system. So this energy has to get out and get to the surface of it. And you could see from the energy output, there's a lot of heat that's built up around the tubings and not at the surface. So we're not able to push that energy through. And you can shows up here on the surface. So this is how much energy is leaving the surface, which actually is put into the room, and here's the temperature. So through both of these, we're looking for a very uniform temperature and energy output. So here it is, same thing with the staple up with plates here with the heat emission plates installed, same type of floor system. So I'm not going to dwell too much on it. Here's that picture of what it looks like. So with the plates, so it's the exact same thing, just with those heat emission plates in 120-degree supply water temperature. We're outputting a floor temperature that's close to 90 degrees. In radiant floor, the design standard is to keep it around 85 degrees. You can go a little bit higher, maybe in a bathroom with tile, you can go to 90, but you don't want to go any higher than that. It's kind of a design thing. And then if you look at the outputs, right? So here's the temperature outputs per, fairly close to being uniform. And then when we look at it here through the energy output, it's pretty uniform. The heat built up is not significant, right? In that other slide, you could see a lot of heat built up here. And there's not a lot of heat being built up here. And the energy is actually being very directed up and out of the floor system. So you can see there's a lot of energy built up on the top of the, on the other side of the heat emission plate. That's where the energy is being directed. We're just back to this slide really quick. Energy is kind of trapped, right? And that's why I would call this a high mass system, because you can just see this very high amounts of energy and high amount of temperature. These are the exact same scale. Well, the scale may be a little off. I think that's 120, and this one is this one's 120 as well. So you can see that just the difference in the energy being trapped, the temperature being trapped, and then the energy being trapped here, and how it's being directed out of the floor system and into the room, which is where we want it. So then the next one is that plywood subfloor with aluminum cover. Pretty much a standard, same type of system. Subfloor, I call it 3/4. I think that's an error in the slide, but it's a little bit thicker here because that's just the way the subfloors are built. But again, this is the tubing impregnated in that aluminum skin that goes over the subfloor. So it's right up next to where the finished floor is going to be. So if we look at the output on that, a very uniform temperature distribution across here, right? You can see that there's not a lot of heat built up in the floor system. Energy is being directed right at the floor, the plywood, not the plywood, the hardwood covering, being directed out of the floor system and into the room. So this is performing very well. And you can see with the 110-degree water, we're running a little bit of a hotter floor, but the energy output is very uniform. And we can go look at the high mass system, lightweight concrete system. So here we have the subfloor, and then above that we have 1.5 inches of concrete, and then the tubing is just sitting right here on that, and then the 3/4 hardwood over the top of it. So 110-degree supply water, and you can see we get a very uniform temperature out of it, a little bit of gradient, but not much. Energy output looks really good. However, you can see the energy temperature is trapped within the floor system. Again, this is why I'd call it a high mass system. It's not going to want to change temperature fast. All this, there's a lot of energy that's trapped, or heat that's trapped within the floor system. You could see very localized energy within the concrete system. So it's all trapped right here and here, being put out to get to that floor system. So in a tabular, in a tabular format here, we ran a bunch of different runs, which is the FEA. So that's when we can get that output. And again, we're looking at floor temperatures here, and this is the average across the floor surface temperature. But if we go back in the slides, right, we can see that, average here, right, we have a high band and then we have a low band. So energy isn't coming out as fast, where, once we get into a little bit higher performing system, those bands get less and less and less across, so that we get a more uniform surface temperature, and that allows more energy to flow out of the system and into the room, which is where we want it to go. So just looking at this, right, so the staple up with no plates, we get 8.66 BTUs per hour per square foot output at 170-degree water temperature. Gives us an average floor temperature of 86.31, and then we lose 1.34 BTUs out of the bottom of the floor system. That's all that energy being trapped in there. Again, we've got to do 170-degree water temperature, which is really high. A boiler system or whatever, Today we design a lot with heat pumps with electric heating, and so this just does not work with electric heating efficiently to do a staple up. I wouldn't recommend anybody do a staple up system. This is old technology. It's very low outputting, takes a high water temperature. It should be avoided for a high performing building. I would not consider high performing building to use it a staple up, and DMA's philosophy is not to design with staple up. We will not design staple up systems just because they perform so poorly. The next one is just staple up with heat plates, 120-degree water. Again, we ran it the higher water temperatures. I'm not going to spend too much time because the floor temperatures are too high, right? We need to be in that 85 floor temperature. But as you can see, as you run it, you get a higher output. You lose more to out of the bottom of the floor. But again, the floor temperature is the governing factor here. And with an 86-degree floor temp at 120-degree water, you get 18 BTUs per hour per square foot out. Very respectable output. Most systems can be heated with this. But again, you're running 120-degree water temperature, and that's at the upper limit for most heat pumps. So if you're doing electric heating, that's kind of up at the upper end. You're going to lose efficiency at that 110-degree water using heat pumps. A boiler system, that's a perfect temperature to be running with. So a gas boiler or an electric boiler, that system will operate well at that 120-degree water and give you enough output to meet almost any building loads with good building construction today. Then the energy you lose out the bottom is 1.54. So, it's not as much as the staple up with no heat plates. It's a little more, but it's not significant. I want to be concerned with that. Now we go to the warm board again, and we ran it at higher temperatures. Again, the floor temperatures are just too high. At 170-degree water, you get an extreme amount of output. It's just uncomfortable to walk on. So if we look at a temperature that actually makes sense, at 104-degree water temperature, you get 17 BTUs per hour per square foot out of it, and you lose 1 BTU per hour out the bottom of the floor. That's a pretty respectable number. You could actually go to 110. Floor is starting to get that little high number there. And this is, again, with plywood. If you're doing carpet or something, you can actually play around with these numbers. But, with the hardwood floor covering, that's where we're at 89. Starting to get an upper limit that you may not want to operate it at that, but you get 20 BTUs per hour per square foot. So that's pretty good. Then we look at the lightweight concrete. At the same 110-degree water, you get 17 BTUs per square foot. So they're pretty close to the warm board, 86-degree floor temperature, and about the same energy out the bottom. And then at 104-degree water temperature, you get 14.5 BTUs per hour per square foot out. At 83.67 floor temp, so 0.9 BTUs out the bottom. So those are the two differences there. Now, there are some things here. We modeled these on 8 inches on center for the warm board. I think warm board's actually at 9 inches on center. And here with the high mass system, the concrete, you have a lot of flexibility, and this is 8 inches on center, and you could actually go down to 6 inches on center, and you get a little bit more output out of the two. But as you can see, the high mass system here has more heat built up, very localized, where here you don't have that same heat built up, and it's not as significant, right? There's a lot of just heat built up right here. There's more energy to the surface. This the system here, this lightweight system, is going to react faster to temperature changes. So the more, the water temperature in the floor is going to be able to change this floor surface temperature faster. The high mass system, because all this energy is built up here, it takes longer for that energy to get taken out of the floor system. So when we have in the Front Range of Colorado here, when the weather changes quickly, in the fall and the spring, with the high mass system, you can overheat the room fairly easy. If you don't have like outdoor air resets or all those other things going on within the system, this here, the low mass system is going to be able to change temperature faster than you can get with the high mass system. So those performance-wise, these are the big difference between a high mass system and a low mass system. So typically is what we're pushing more to is these low mass systems going forward, because they do react so much faster, and we don't need to have the heat built up into the floor systems because we don't build as drafty buildings that we used to have back in the old days, where, you know, a drafty building with all the air leakages, the high mass system had the advantage because it didn't change temperature. But now with buildings being so much tighter, we don't have as much drafts, the low mass system actually can perform quite well. This was a brief thing on just radiant floor systems. I went through it, I hopefully fairly fast or fairly slow, but in the instance of brevity, I kept things kind of at a very high level. If you need more information or have a very custom radiant floor system you would like to discuss, or you got a custom home or luxury residential, you can reach out to me at Steven F at DMA Engineering, dma-eng.com. Phone numbers here. I'll get you to our switchboard, and then this is our Front Range officing here in Colorado, in Golden. We also have an office in Basalt, Colorado. So anyways, thanks. Hope you enjoyed the video.